Okay, Chan Physics, just doing a quick video here on heating and cooling curves because to do all of the Unit 7 work, including the calculations that we'll do at the end, we need to be able to understand what's happening in a heating and cooling curve. And so this problem set that we've been doing, this is the key, and I just want to go over it with you guys if you're misunderstanding or not understanding what's going on. So the first one is basically what they're doing is this is what we did in the lab. We had ice and water. And so ice and water looks like this. Ice and water together looks like this on this part number one. And this is where the ice is melting. Until we get to the point where the ice melts, the temperature shouldn't change. So the ice, as we're adding heat, it's heating up the whole substance of two things, and it's concentrating on breaking down the bonds for the ice. And so once all the ice is gone, then right here in section 2, now the heat that's coming from the hot plate should be able to raise the temperature of the liquid. And that's where we got about right here, about 97, 98. It should be 100, but that's just the way our thermometers are working. And so then we get to 97, 98, and then we started boiling off the water. And we never got above 97 or 98. And so the water just keeps boiling away and until we get to the end here. So this was the lab, and that was the whole idea of this lab right here. And so the phases that we're seeing right here is ice and water, just water, and then here we have water and vapor. So that was the whole point of these questions here. And you can look at these questions and understand, learn the words like melting and freezing and things like that. So then we wanted you to do is we wanted you to picture what it would look like for those different parts of that heating curve. And so here we have water, and see the water is in a lattice. So we see all the pieces are like together in like spots, right? And they're shaking. So these things here are suggesting they're shaking, not that they're moving. And so, and you can see that the ice stays off the edges, so it's not filling the edges right here. And then here you can see that it's all solid and it's zero. So then we get to the edge of that thing. So we just moved from this side right here where it's all ice to this side where it's water and all the ice is gone. And so then they asked you to draw that. So here again, we're still at zero, right? Because at zero right here, this is 0 degrees right here. So we're still at zero, and we've got water. Now the water can move, so it's not shaking anymore, but it's got the arrows. And the arrows are relatively short to demonstrate that it's 0 degrees. So now they say, all right, move from area 2 to area 3. Now we hit 100 degrees. So what does the molecules look like? Well, they're still down in the bottom right here. So they're still liquid, but they have longer arrows to demonstrate that they are hotter. Okay, so it's 100 degrees. And then they said all gas, and so we see all gas filling the entire area. So we've got not just stuff on the bottom, but we have stuff filling the entire area. Okay, so then they ask you what's happening. And this is important, and a lot of you guys are just like copying down what it says here, or maybe you're not even doing it. But it's really important that you understand the three questions that they're asking. They're asking about what is the temperature, therefore, what does it look like in the molecules, and then what kind of arrangement are the molecules in? And so those three questions: temperature, what does it look like, and then what's the phase? And so you can see the question always answers those questions. So the phase is changing in area number one. So we've got we're just melting the ice into water. So the phase is changing. The solid particles have attraction, right? These attractions right here that make them all like this have to be broken. So the heat is being used to break these bonds right here to make this happen. All right, so there's a attraction between them. And then the particles of the solids start popping off and moving around, but then they have container. But there is no temperature change here, no temperature change. And so we see the temperature does not change. And so those molecules go from shaking to just the small little area. So and then region 2 right here, we're going to get right here, we're just all liquid at 0 degrees. And so the temperature is changing in section 2. So right here we're in section 2 as we're moving up. And so what's going to happen in section 2? We're going to go from 0 degrees to 100 degrees. What does that look like? Well, It just looks like the particles should get a different speed, and so they'll have a bigger arrow, but there is no phase change. And then now when we're in area 3 right here, well, now we're at the same temperature, so the temperature is not going to change. The We're going to start with a liquid, and we're going to end over here with a gas. And so the question just says the phase is changing, so the temperature doesn't change, and we're going to be breaking those bonds, the liquid bonds, into gas into gas. So the next thing they ask us to do is like, let's say, well, let's see if we can expand this. And so what you guys had before was you had 1, 2, 3, and so they're going to add the 0 and the 4. These are things that we could not do in the lab, and so in the lab we really couldn't get a thermometer to measure ice that was below 0, but it happens. I mean, you can definitely take ice at 0 degrees or at 32 degrees Fahrenheit, 0 degrees, and you could get it colder. And so we can just, put it outside. It's going to get colder and colder and colder. So it can get below 0. Ice can get below 0. And so that's what this 0 is supposed to show, is that ice can change from a negative number towards 0. And then we can have that phase change, ice changing into water right here. And that's a phase change, and so the temperature doesn't change. And then we get the water heating up. So now the molecules are just getting faster or being bigger arrows. And then we hit another plateau right here where all the heat being added is used to change the phase of liquid into gas. So all the liquid into gas. And then if we could, in the lab, if we could trap all that gas into something, we could actually get it hotter than 100 degrees. We can make it move faster. And so that's what the whole the 5-step or the 5-ladder heating curve looks like, right? And so that was what they were asking you to do. And then they said, well, could we do it opposite? So could we change it around where we took something hotter, take a gas that's hotter than 100, and then cool it down to 0. And then once we do that, well, then we would condense it. And then that condensation would be from gas to liquid. And then right here it'd be all liquid. And then we'd be able to cool it down from liquid into ice. So now we can start making ice. And then it takes a long time for, once we hit the 0, for it to actually freeze and become that lattice. And then we could make it colder. And so this is what we call a cooling curve. And it's just the opposite. And so that was what they asked you to do. And so what's really important, though, is that you read through each one of these and know that you understand what's happening to both the phase and the thermal energy. So the phase is whether or not it's a solid, liquid, or gas, and the thermal energy is whether or not it's hotter or colder. And so if we were to go through here, right here, we can see that they added these things. So right here, as we're changing from 120 degrees down to 100, we're changing the thermal degrees or the thermal energy. So we're only changing the thermal energy, the temperature. And here then, when we get to 100, well, now we're going to change the phase. So we're going to it's going to take energy out to get from a gas to a liquid. We're going to have to pull more energy out of that to have it condense. Once we have it all liquid, well, now we have a 100-degree liquid. We can pull energy out to make it into ice. And so that's thermal. That's a thermal change. And then here we have a phase change. So a phase is from liquid to solid. And so this is the freezing. And then once we get here, we've got a thermal again. And what you're going to see is that this is where we're going to build on equations, because we know how to equate the thermal and we know how to do the phase. And so if we give you something like, if we give you water starting at 120 degrees and we cool it down to 50, we're going to ask you to determine how much energy was needed to be pulled out of the system or out of the water. And so you're going to have to take the phase change here as a gas. So, I mean, the thermal change right here, and then you're going to have to do the phase change from gas to liquid, and then you're going to have to do the thermal change here as a liquid. And so you're going to have to understand all of those things, not only where you are at the curve or what kind of change you are, to be able to do the calculations. And if you don't understand that, then it's going to be impossible for you to pick the right equations. And so that's what we were doing here right now. And then the last thing was, if you made a heating curve with a different substance like iron, what similarities and differences would you see? So we've been using water, so we said the boiling point is 100, but we never put 100. We never put the melting point as 0. So what do you think with iron? Well, think about it. At room temperature, iron is a solid. So instead of having it as a liquid, because water is a liquid, we would think that the melting point, or the 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 part where we go from a solid to a liquid, would be much higher. So probably in the 100 or 200 degrees. So this graph would shift up, because the melting point would have to shift up. And of course, then the boiling point, if you've ever seen a boiling point for iron, it would be pretty high, right? And so we'd have to have, instead of 100, we'd have to shift it up. But the relative shape of the curves should stay the same. And that is that, the same idea that you'd have to break bonds from solid to liquid here, or you have to break bonds right here from liquid to gas if you were heating this up, or if you're cooling it down, the opposite. So the differences are that these points, the boiling point and the melting points, would be shifted up. The similarities would be, it would be the same shape. All right. Hopefully that helps you if you are still behind on this. But thanks for watching, and we'll see you in physics.